My name is Keith. Some of you might know me, most of you probably don't know me, and you will never heard of a company called Nokia. We do not make phones. We are internet technology provider. Our business is B2B. We do not sell. Whatever I'm presenting here is not for sale for common people. You cannot buy in the shop. Only some tier 1 customer can buy it, okay? And I'm going to present something today is about our technology-wise. I'm not going to present something product. I've been told not to present that. So it's technology-wise, and we are, the technology I'm going to present you is by a research project in Bell Lab over 20 years ago. We've been doing the research and development for quite a long time, and we have been working very hard. They're mainly deployed in Europe and Latin America, and in UK is zero, other than me and my friends at home. I have around 3,000 channels at home, okay? So if you want to watch TV, you can come to my home, bring the beer, please. And we can shout before all other people watching the football match. Okay, because I will guarantee you 2 seconds ahead of time. So, Nokia, we've been working very hard for the IP IP broadcasting. What I'm presenting you is the IP broadcasting is not on demand. Okay, it's for linear TV. I will try to avoid to say the word called AI. What I'm doing in here is driven by data, intelligence, learning-based, and predictive, and adaptive, and content, and network awareness. Okay, so it senses an environment, and it acts and behaves according to the network condition and the environment. Once upon a time, before I was born, 1962, Bell Lab built something called Telstar 1. It's the first satellite. It transmits the broadcast TV over the sky somewhere above our head, and then transatlantic. And also recently we've been doing so as well over IP. The first one who ever saw that demo, I think some of you might know him, called Don Robinson, and ask him where he saw the demo. Okay, it's in Boston. So with the spirit of the Telstar, we are driving, inspired us to drive toward the internet broadcast. The objective is going to be similar experience as the broadcast TV, as 7 nines is broadcast grade, and resilient, reliable, and can reach everywhere, anywhere over the internet as far as there's enough bandwidth. So what are the challenges in distribution broadcast TV over internet? First thing, we try to use the TCP, which was invented 50 years ago. When I was a little kid, I learned about this. It's a latency, okay? Using TCP will introduce head of line blocking. So if you lost one packet, you will wait forever to get the packet back, to arrive back, okay? So I asked one of the guys in BBC the other day, I was in a meeting, and I asked him, if you lost one packet, how long will it take to retransmit that? He gave me a very honest answer. It's from 1 second to infinitive. Okay, that is the case. Second thing is scalability. So WebRTC is very reliable. It can send it, literally is less than half-second latency, but it cannot scale. Resilience, okay, with MOQ, meteor overquake, quite a lot of hype at the moment, and the performance quite good, and I tested, and more than 5% of random packet loss, it just lost, okay. And then reliability, we try to use RTP, and I've done all this testing as well. It very good in retransmission up to a certain point, but after a certain percentage of packet loss, it just lost. Okay, so opportunities that we are going to use the RTP base. And to route the multicast, it's not the multicast you know. We're using SLV6 multicast. So it's segment the route the multicast. So we only distribute the multicast broadcast to wherever you need, not flooding the whole entire internet. So this is a new standard. It's coming out into IETF standard, and we are helping that to draft that. And also we use a route unicast, so it doesn't matter where you are, as far as you have internet connection and you have an IP address. So we are using the enhanced with predictive and adaptive and smart streaming based on deep reinforcement learning. Okay, I will try to avoid to use the word AI because that is the technology we are using. I tried to get my professor to come here as well today, but unfortunately, and he need to go to the Strictly Come Dancing. So I lost that. I cannot compete with them. So it's very resilient. The problem now we can see that we can have the channel change. We compare with different technology. Our solution comes with the fast channel change is under 90 milliseconds to 350 milliseconds, approximately half second, let's say that. And the comparison with all the different distribution technology, we are more or less similar to DTT and satellite, sometimes even faster than BBC One. So we use LTP with DRL, not DRM. Okay, please do not confuse that. DRL is the deep reinforcement learning. For the retransmission, we classify the loss type, the behavior of the packet, and then we build the data model and predict an adaptive recovery, and then sustain the payback at over 40% of random packet loss. With the round trip time is around 1.3 seconds, that means that we can go to the moon and back, hopefully. And we need to look for a volunteer to go there. And stream switching, so we can switch the channel under 500 milliseconds. We tested with the VR and the XR, so you can just turn your head and then we can change the channel, but actually it's only single view, and then it looks like multiple view and 360 degree as well. Smooth multi-bit rate adaptation, so we sense the bit rate changes of the capacity on the network, and that study has been done by also someone else in Concordia University, was presented in the My High video this year, early on. So it's no payback drift. So you start with 10-second delay, you will have 10-second delay after the full football match. Not after football match, you have a 2 hours delay, okay. LTP, we use the route multicast and route unicast. So the route multicast, we can scale massively, okay, to everyone. So if you, as far as you have the internet, we can send it by multicast to your home, okay. The route unicast fallback, so we use a unicast assist the multicast, not multicast assist the unicast, with inverse of what they're doing. So this way, we can accelerate the channel change, we pair the packet. If the network cannot support multicast, we fall back to unicast, okay? Because not all the network can support multicast. We predictive and adaptive switching across all the networks, for example, Wi-Fi, 5G, satellite, and HAPS, high altitude platform station. We've been tested that somewhere in Scotland, and that's real fun. So the challenge is that the Wi-Fi native multicast is very inefficient, very low bit rate, and also the 5G network, some of them, they support multicast, some of them don't. So hardly anyone knows that what is going to be late in the future. So what we do is that we have been doing that. So we do the multicast to unicast conversion, which is supported by standard, IETF standard, since 2006, okay? Because we helped them to roll that standard. So it's the MC to UC, and most of the Wi-Fi home gateway, they do have the MC to UC as well. So you have arriving the multicast at the home gateway, it automatically translates into the unicast. You do not need a client proxy on the home gateway to do the job, such need the home gateway. It does that translation laterally. Okay, it's the part of the standard. And also we can do the 5G and 4G, 5G network as well. So if the edge can support multicast, we send over the multicast into the 5G network. If not, our service router will get the feedback from the device, playback, say, I cannot receive multicast, can you please send me unicast? Just one command, okay? And the result is that it's unified approach, smooth, reliable, HD and Ultra HD delivery across Wi-Fi, mobile, fixed network, satellite. I will show you a demo on the satellite. And hubs, okay? Under the congestion condition, it automatically sends the bit rate, and then it learns the network condition, it drops the bit rate, okay? The paper being published by Professor. So we use the, under congestion, we just drop the bit rate or go back up the bit rate, and the detail of that sort of a hybrid adaptive learning is published by ACM as well. So this is our overall architecture, and we can go over the broadband, Wi-Fi, internet, go to a satellite, as well as the in-flight Wi-Fi. So you can bring your own device to watch TV, and I demoed that to one of the very upset customer who watched the Formula One, and he couldn't see his Formula race, and I showed him on my mobile phone, and he said, how the hell you get that? I can't. I said, wow, you use the wrong technology. So I asked him for £2,000 to watch a half-hour race. And he told me to get lost. Okay, how it works? Okay, it's very simple. We just put the MPEG transport stream as it for the broadcast TV. Just imagine that is HLS, it's very infinitive segment, and if we send it FPS 20 to 40 milliseconds, one single chunk. That is a simple explanation if you only know how to use the HTTP streaming, HLS. So we just send it to stream to the edge, and then from the edge, it does all the intelligence. So the client will send the request, say that I need to join the channel, and then the server will send the unicast to the device over NAT, okay, network address translation. And then it will, because we can manage the NAT, so you will send back to the device, the stream, and then etc. until it join the catch up the multicast. So the device will have the buffer of the encoder buffer. Okay, I'm not sure how many people knows about MPEG transport stream. So if you know about MPEG transport stream, the device have to be buffer at least the MPEG transport stream buffer is by the encoder. So it's the PTS minus PCR if you want to more technical. Otherwise, you just fill up the buffer, and then you will fall back to multicast. So this way, you will not consume the bandwidth. Okay, so one single copy for everyone. If the device reply say that I cannot join the multicast, and please keep sending me the unicast, the server will just replace the S and G, source and group, of the multicast stream with the destination IP address and the port. This is the standard, IETF standard, and all done by the service router in your network already. In UK, approximately 95% of those routers are Nokia router, and they do this already. Okay. So that's how it goes. If you say that my device only can support XLS, dash, etc., multi-DRM, so what we do is that we put OCI, Open Container Initiative CDN agents, into the device, either your mobile phone, your home gateway, or whatever, your Raspberry Pi. We developed this using the Raspberry Pi 2, so it's a very low power, so you can test our capability. So you can imagine that it's just like a CDN in your pocket. So you eliminate the data center, you eliminate the electricity bill, you eliminate all the caching, just sending the live channel, just like everyone, just like your normal TV nowadays. So we focus on how to get A to Z, okay? without any cost on the guy who in the middle transporting it. So this way we can backward compatible. So when you arrive at the edge, you can also multicast it out. Okay, this way you can deliver to a ship somewhere in the middle of the ocean, and then you go to everyone, or in the airplane or wherever. Okay, so you can. So case study. Now let's go from design to the real world in the live sport and major tournament and in-flight Wi-Fi streaming. So we have done some comparison. DTT, DTH is in UK because I've been streaming from our customer from different locations in Europe. And from broadcast TV, I checked it with the time dot. What time is? Yeah, that website is you just ask what's the time now, and then you compare with the time difference between all the screen. I do not put all the screen in the same place, so I test each screen at a time, so you compare with the real-time clock, so this way you can have a good reference what happened. So OTT XLS and Dash, it gives some, this was last year, is 67 on the iPlayer. I'm not testing the Sky Glass because I've been told do not test it because we all know that latency. So even the shop sales executive told me don't buy it, keep my Sky Q. So I've been keeping my Sky Q very hard, close to me. I say I'm not going to let it go. Okay, and then we compare with the broadcast TV with our solution. We realized that we're 2 seconds ahead. I was wondering what's happening. So I just checked that because somehow the broadcaster need to go up to the satellite and then come down and then we broadcast it. So that will introduce quite a lot. The drifting is the major killer of the OTT. Okay, using TCP technology, when you have the one packet loss, you wait for the packet to arrive because it's a perfectionist. Okay, TCP is a perfectionist. It's not perfect, it's not going to happen. So it drifts over 200 seconds. It's under poor packet loss is quite bad. And our solution, we test up to 40%. If you want to see it, we have the upstairs, and we have the impairment too, can stimulate all sorts of network conditions. So this one was tested a few months ago, and when I was in Bristol, in BEAM, Bristol Media Entertainment Mixer, and the guy who tested come and saw the demo, and then we used the simulator, simulate 40% random packet loss compared with BBC One, and we are zero drift after 2 hours. Okay, and then I set the impairment to up to 60%, it still works. And the guy called Adrian Rowe, I think some of you know him, and he didn't believe it, he unplugged the cable, he said, this is real, okay. So I miss him because I asked him to come along to unplug the cable today, and he said someone else can do the job for him. Okay. And he was the one of our 50 people in the meeting who understood what was going on in here. So it's quite scary. Okay, a lot of people not knowing the TCP against UDP and retransmission. Okay, that's we need quite a lot of education to be done. So this one is was in July when I flew from Heathrow to JFK, and in-flight entertainment using satellite was come from Starlink and SES, and they using BA using Starlink. It's quite good. Okay, when I told all the people, say it's a very good internet connection on the plane. They say everyone complaining. What's wrong? I said, oh, okay. And again, that's a problem. It's the TV has come from Germany, from Cable Deutschland, on my mobile phone, and then I watch that everywhere. And this is the test result we have done. We compare with the test condition is random packet loss, more than 30%. And the round trip times on 400 milliseconds. And the TCP just stopped. Okay, if you know the TCP transport, you must know the guy called Mattis. Okay, in 1995, Mattis and his friends wrote a paper about the formula called Mattis equation. It explained that what happened to the TCP packet if you're facing packet loss or round trip time. Over 10% of the random packet loss, you can stop the TCP if you're using 2 segments, MSS, media segment size. If you're using 24 seconds, you might get around 2 or 3 megabit. If you're over 30% packet loss, you have no internet connection. Okay. So we test that with the RTP using DRL. So we have the test results that without the DRL, we only can support 3 to 10% random packet loss if you use the standard RTP retransmission. Okay, missing a packet request, and without any protection or profiling the condition. With a fixed time period, it might be better because you learn how to handle that 30% loss. With DRL, core type, okay, DRL have typically two types. One's the core type, is the basic one. One's a more advanced type, that is more complicated calculation and neural network. We need to use the NPU, it's neural network processor, to handle the advanced type. Okay, so that is quite scary, and we cannot find anything. So we are trying to make it work by giving more time to learn. Okay, so after learning, we put the data back into the model, into the set-top box or player, our library. So this way we improve the capability. So without protection, we handle up to 30% random packet loss. With protection and learning, more advanced learning technique, we can handle more than 30%. After a prolonged period of learning, it can handle up to 65%. So that's what when Adrian unpacked my cable, because he couldn't believe that 65% of random packet loss is still working. Okay, actually we went up to 80% random packet loss, and it was working. He said, "Do you really using the cable?" So he unpacked the cable, and he saw that stop. So this is one of the example of 40% random packet loss, and we have around 12 packet behind. So it depends on the sample rate. And this is a 50% cycle of 1 second. Actually, we can handle up to 1.5, 1.6 second of no packet, and then 600 milliseconds of connection of the cable. So we have the simulator in here as well. We can do that. So this solution is not something out of the lab or in experimental stage. We already in deployment in major tier 1 customer. And we also won the best in broadcast distribution goal, and we beat all the guys in here. I think some of you are working for those companies, so don't get angry with me. And we just entered and we won. Okay, we didn't know about who entered the competition. And this year we been shortlisted as well. Okay, so we have shown we have also introduced some new technology and technique in this year. So they love it, and so let's see what happens next. So in conclusion, the solution is that it's as fast, as reliable as TV what you can watch now, not the OTT internet TV by someone. It's the standard DTT or DTH with all the enhancement. We can have a latency matching the broadcast TV, and as reliable and resilient under very long round trip time and packet loss, because we find a way to avoid the DTT, RTT problem. And it's very scalable. It's one stream for everyone. So we can use a multicast and segment route multicast to handle the distribution rather than putting more cache server, distribution server, which burn your money and burn your pocket. and it's not very healthy, and so we can avoid that. We can use it in fact, bring your own device, streaming. So this is the demo we set up, but the internet in this building is terrible. It can range from 60 megabit down to 0 in no time. Okay, so someone unplugging the cable, probably doing some testing. F is only 2 megabit, and our customer do not stream 2 megabit Ultra HD, so at the moment it's quite challenging to do the demo. This is what happened is that we send it via public internet from Copenhagen, Frankfurt, Lisbon, and Madrid to here, and also from somewhere in Switzerland, somewhere, okay. And this one is from Copenhagen, the demo in here is LDK. Okay, it's a Comcast platform, LDK, and you can just take the LDK 8 and you can just unpackage it, and then you put in your LDK platform, it will work. Of course, you need to buy the license from us. Okay. And it works with the mobile phone, set-top box, or whatever, smart TV. We've been working together with Samsung, LG, and all sort of brand TV since 2010. Okay. Telefonica was the first one who put that into the Samsung Smart TV since 2012. And the problem is that it's not cheaper than the set-top box, okay? And the Samsung Smart TV is more expensive than the set-top box. So in the end, they went back to the set-top box business and rather than on the TV because it's too expensive, it's not economical. So I'm happy to take any question. Thank you for your attention.